morning, everyone. Happy Friday. Happy May. We are kind of just in the beginning stages of learning about root locus diagrams, what they can do, how to build them, and eventually how to use them to help us design systems from scratch. So I'm going to switch over to PowerPoint now. The big picture, or what a root locus diagram is simply said, a sketch of the complex plane that contains all of the possible closed loop pole locations as one parameter within the open loop system changes. So usually that parameter is going to be the open loop gain K. And we are going to get a couple of glimpses at where these closed loop poles can be, and then we're going to make an educated guess about how the closed loop poles could travel from one of our glimpses to another. The key to all of this is understanding that the open loop transfer function tells us everything that we're going to be able to find out about the closed loop poles. And that I don't expect to make a whole lot of sense at first, but if I keep saying it, I hope you'll eventually believe me. So to review, the open loop transfer function is defined as the product of all the blocks around the loop. And if you define that open loop transfer function in that way, then any S, any value of S that is a valid closed loop pole must also be a value of S that produces -1 when plugged into the open loop transfer function. So the open loop transfer function is in general a complex to complex mapping. And so therefore, we can break this L of S hat equal to -1 into two statements, that if they are both true, then we have an S hat that can be a closed loop pole. And those statements are the magnitude and the phase criteria. Any S hat that makes the magnitude of L 1 and makes the phase of L plus or minus 180, that S hat is a valid closed loop pole. And remember, L is the open loop transfer function. So I'm making a statement about an argument to the open loop transfer function, and I'm putting a test on that argument. And if the argument passes the test, that argument must be a closed loop pole. Okay, so that is a mental leap that is difficult for a lot of people to make. So the very first reason, or the very first glimpse we're going to get at where the closed loop poles can be as K changes is from the argument presented on this slide. So this was the question, what do the open loop poles and zeros tell us about the closed loop poles? So if you break up the open loop transfer function as a numerator polynomial and a denominator polynomial, then I wanted to be clear that the S's that make n of S 0, we'd call those open loop zeros. And the S's that make d of S 0, we'd call those the open loop poles, because they are the zeros and poles of the open loop transfer function. So I am going to suppose that there exists an S hat that is a closed loop pole. That is equivalent to saying there is an S hat that makes L of S hat equal to -1. Now, if you do a little bit of algebra gymnastics here, you can get L of S hat equal to -1 equivalent to two statements. D of S hat plus K of N S hat equals 0, and if you divide through by K, D over K plus N equals 0. And I'm going to use both of those for different reasons. In the first, if I let K become very, very small, essentially 0, then the only S hats that make this true are those S hats that are open loop poles. So now we can start getting into the new content today. S hat is an open loop pole and a closed loop pole, right? Because we suppose that S hat was this is equivalent to saying S hat is a closed loop pole. If you take the opposite approach, if you go to this last statement and let K get very large, then all of a sudden the denominator polynomial has very little weight and the numerator polynomial has all the weight. And so that means that the S hats that make the numerator 0 are going to be the closed loop poles. And we just established that those S hats that make the numerator 0 are open loop zeros. So we've got two balancing acts going on. As K is small, the closed loop poles approach the open loop poles as k gets small. And as k gets big, the closed loop poles approach the open loop zeros. Any questions on that? So I'm happy that we got to go over this slide twice because I don't think it's at all obvious what is going on here. So any questions now that you've seen it twice? Okay, let's see how that works for our running example. So remember, if you go back one slide, the running example was this closed loop system with a variable open loop gain k. And so the question now is, where are the closed loop poles of this system when k is small and when k is big? Well, what we just showed is that the closed loop poles when k is small must be near the open loop poles. And so the answer to this question is simply draw the open loop poles. We had them at -1, and we had them at -3, and we had them at -1 plus or minus j. Okay, so the answer is, where are the closed loop poles when k is small? Near the x's. How about when k is big? Well, we said that they're going to approach the open loop zeros. So near the 0. And here we have our first kind of problem. There are how many closed loop poles? Just bulk number. If you go back to this slide, how many closed loop poles will there be? What is the order of this closed loop system?
Would it be 4?
That's right. That's right. So down here, the L of S is going to have a 4th order denominator. And if you move that over to the 1, you're going to add a 4th order polynomial with a 1st order polynomial, which is a 4th order polynomial. So if I go here and I note that there are 4 closed loop poles, there are also 4 open loop poles. That's nice. It didn't have to be that way, but it is that way in this case. There's only 1 open loop 0. And so this is what was not communicated on the last slide, is that there are other possibilities. The other possibilities are that the absolute magnitudes of the pole locations could themselves become infinite. So the other side to this coin is that they're going to be near the 0 or very large in magnitude. I will commonly not say very large in magnitude. My favorite way to say this is that they go off the page. So the other way that this expression can be made true is if d of s hat itself gets infinite in magnitude. Then the k going to infinity and the d going to infinity, they can actually balance each other out. And you can also get this expression equaling 0 for s's that are not open loop zeros. I want to use this as a plug for the resource that I have posted on Polylearn. When I first read the textbook that is being used with this class, I found that it was a little bit lacking in the derivations for some of these rules that we're going to learn. So I would classify the textbook and the lecture as being comparable in terms of technical depth. But I remember when I took this class and I learned these rules, I learned them at that kind of just surface information, just surface depth. And so I wanted to provide you with a resource that goes a little bit deeper and gives you some of the mathematical derivations for why the things that both the textbook and I are going to be teaching you. And I'm calling that the root locus summary. And it's basically a chapter of a textbook that I wrote and I posted it to Polylearn. So if I ever say something in lecture and you're wondering why exactly that's true, I really do encourage you to check out the root locus summary PDF that I've posted to Polylearn. In particular, it makes the statement that I just had, where the S's get large in magnitude, it makes that much more rigorous. I would say it even proves it.
Quick question.
Go ahead.
So what if it's both near the x-axis and the 0? Then what is k? Is it small or big?
It's going to be in between. So we're going to show eventually that if you suspect a closed loop pole to be here, then that'll mean that if it's true, it'll be k as some intermediate value. And we'll get much more in detail about that in the coming, I think, hours of lecture. But for now, the only thing we know is what do the closed loop poles do when k is small, close to 0, and what do they do when they're big? But we're going to fill in the gaps as we go along. So speaking of which, let's see if we can do a little bit more filling in where the closed loop poles can be. So I would like to check whether this point, which I'm going to call S1, S hat 1, could S hat 1 be a closed loop pole for some positive k? That's the question I want to ask and answer right now. And I just picked that. So technically speaking, you could do what I'm about to do for any point in the plane, and you would get the answer that you would get a yes or no answer. There are, of course, an infinite number of points in the plane, and some of them make this following analysis more difficult than others. So I've picked a relatively easy point for our first, what I'm going to call a test point. So this is a test point. And the idea is I'm going to try and test whether this point can be a closed loop pole. So we have two criteria for S hat to be a closed loop pole. The first is the magnitude criterion. So that says, is the magnitude of L at S hat 1 equal to 1 for some k? What do you think? You have a sense for this? Maybe we need to write out the magnitude of L of S. So remember that this example, we had L of S was k, and then S plus 2 up top, S plus 1 on bottom, S plus 3 on bottom, and then the complex conjugate pair. And so if I want to evaluate the magnitude of this at S hat 1, I just replace all the S's with S hat 1. And then I take the absolute value. But what we've got here is a whole bunch of products, right? And I'm going to use the fact that the magnitude of the product of two complex numbers is the product of their magnitudes. And so what we've got is the absolute value bars that lie around the entire fraction actually can be moved so that they are around each and every factor. Okay. So this is equivalent to the magnitude of L of S hat. So tell me now, is there a k that makes this 1? And I will wait until I get an answer.
There should be, right?
There should be. Regardless of the exact numeric value of S hat 1, everything here, once you plug in a fixed S hat 1, is going to give you some magnitude, call it x. And it'll be a positive number. All I have to do is pick k to be 1 over x, and I've satisfied the magnitude criterion. Do you follow that? So we can replace this question mark with a check mark for any possible S hat. So again, I'm taking the magnitude of the transfer function. That's where the magnitude bars come from. And we're now got to check the phase criterion. So we only did half the job, but my point here is that this half of the job is actually very easy to satisfy. Because this giant blobbish jelly bean is going to have some magnitude, and I just need to come up with a positive k that has the reciprocal of that magnitude, which is easy to do, and then the product of those two will have magnitude 1. Okay. So the next step is, does it pass the phase criterion? So let's review what the phase criterion is. We are looking for, does the phase of L of S hat equal plus or minus 180? If yes, then it will pass both criteria, and S hat, S1 hat, will be a valid closed loop pole location. Okay. So let's check it out. The phase of L is, again, the phase of K times this big old function. So, quick question. Is the phase of a product the product of phases? Can I use the same trick?
No.
Yeah.
No.
No, that's not how phases work. So what is the trick I should use here?
Addition.
Good. The phase of a product is the sum of the phases. Excellent. So this is actually the phase of K plus the phase of the top minus the phase of the bottom, where the phase of the bottom is the sum of the factors down here. S hat 1 plus 1 plus phase of S hat 1 plus 3 plus phase of S hat 1 plus 1 plus J plus phase of S hat 1 plus 1 minus J. Okay. So again, I'm just taking the phase of the top and I'm subtracting the phase of the bottom, and where each of the phases of the top and bottom are the sum of the constituents phases. Okay, so now it becomes relevant where I picked the test point. I hope you see that for the magnitude criterion, it didn't actually matter where I picked S1 hat. It could have been literally anywhere on the plane, and I would have been able to make the same exact argument. So there are some textbooks that would tell you that the magnitude criterion is a vacuous criterion because it's always satisfied. The phase criterion is the far more stringent criterion. So given where I picked S hat 1, which is some positive real number, well, that doesn't have any effect on phase of K, does it? Because phase of K doesn't have any S1 hats in it. What is the phase of K?
0?
Good, it's 0 because K is a positive real number. So whatever K is, it's going to be 0. So we get, here, I'll do it in red. This is going to be 0 because K is a positive real number, and all of those numbers have 0 phase. Now, what is the phase of S hat 1 plus 2?
0 as well?
0 as well, because 2 is a real number, S1 hat is a real number. They're both positive numbers. If I add them, I'll get a positive real number. So the phase here is 0. That same argument applies here. Whatever S1 hat is, if I add it to 1, I'll get 0 phase. Here I'll get 0 phase. How about for these guys? This is a bit trickier. Here you won't get 0 phase.
45.
45.
So what if S1 hat were way out far right? If it were the origin, I'd agree.
Is it going to be the tan inverse of the imaginary part over the real part?
Good. So let me show you a graphical way to answer the question I just asked. So let's go here. If I'm trying to talk about the vector S1 hat plus 1 plus J, I can think of S1 hat as a vector, and I can think of the number 1 plus J as a vector, which looks something like 1 over and 1 up. So this is the vector 1 plus J. If I were to add those two vectors, then I can do that just by moving this guy up to the tip here. And so this point is the point s hat 1 plus 1 plus j. Now, I didn't have to put both of these vectors at the origin. They are the same vector even if I translate them around. And so what I'm going to do is I'm going to take that picture and I'm going to translate it over to here. So here's my translated S1 hat. Here's my translated 1 plus j hat, 1 plus j vector. And so here I hope you can see that if I add the yellows, I get to the point S1 hat if I started at this x. And so this is all trying to get you to see that when I talk about this quantity, graphically, that's the same as this vector, this black vector. And the phase of this black vector is this angle here, which I'm going to call theta. So this is not 0, but it's theta.
So it's going to be less than 45? Is that what it's trying to explain?
Yes, it's going to be slightly less than 45 if S1 hat is to the right of the origin. But my point here is that you don't actually need to know the exact numeric angle because of what happens next. Tell me, what is the phase of this term?
The opposite.
Always the opposite. So when I add them, I get a net of 0. So this idea that you can line up these vectors to act as if they were sitting on the open loop pole and pointing at the test point, that's going to become a valuable skill later on. Here it was kind of trivial. You could have guessed it was 45-ish or whatever, but I wanted you to see this skill or this technique because we're going to use it later on. So I guess we're equipped to answer the original question now. Is S1 hat a valid closed loop pole location? Yes or no?
No.
Good. No, because this phase is 0, which is not plus or minus 180. So the original assumption was wrong. So the answer to the original question is no, it fails the phase criterion, even though it passes the magnitude criterion. Okay, remember it has to pass both. Okay, I'm going to clean up this slide a little bit and we're going to try another test point. Okay, so to summarize, this S1 hat cannot be a closed loop pole. So let's try another test point. Let's try, I don't know. Should we try here? Call it S2 hat.
Wouldn't any only real S hat fail the phase criterion?
You are overgeneralizing. You are correct that S2 hat and S1 hat will both fail the phase criterion. So I want to walk you through that. I'm going to change all of these 1 subscripts to 2s. And we actually get the exact same answer. So the phase of K is still 0. The phase of S2 hat plus 2 is still 0. The phase of S2 hat plus 1. S2 hat, the way I've drawn it, is a negative real number, but its magnitude is less than 1. So if I add 1 to it, then S hat 2 plus 1 is still positive and real. So that has 0 phase, still 0. This is some different number theta prime, but this is always negative theta prime. So for S2 hat, also cannot be a closed loop pole because it fails the phase criterion just like S1 hat did. But I want to now get you to see that S3 hat is different. And I want you to tell me what is different about S3 hat.
Isn't the middle between a pole and a zero?
Sure. So why does that change the phase criterion result?
Large enough value to give you a negative on the bottom?
Negative where?
In the in the pole, the denominator.
How many negatives? Because there are 3 terms down here, yeah?
Yeah.
Or 4 terms, sorry. So, I mean, let's walk through it. Phase of K is still positive, that's still 0. Phase of S3 plus 2. S3 is now a negative number between -1 and -2, which means this is still going to be a positive number. And here is the change, yeah? If I take, say, -1.5, and I add it to 1, I get -1/2. So this gives me a phase of 180. This one still gives me a phase of 0. This one, some phase, and some opposite of that phase. And this is the key difference, is because this term, and only this term, flips from a positive real to a negative real, which means it flips phase from a 0-degree phase to a 180-degree phase. So here, the sum of all these phases is 180, and so S3 hat can be a closed loop pole. I'll stop there for questions, because I think this is not obvious to everyone the first time they see it.
So for every, how do I want to say this? For every vertical line of poles going from 0 to the negative real direction, for every one of those that an S hat is passed, you produce 1 extra negative in the denominator. Is that correct?
Let's see, is that an accurate statement? So, I mean, it's hard to say, and you'll see that on the next slide where I've tried to summarize the result here. It's actually really hard to say it in a compact sentence.
Sure.
But you are correct that we're only talking about test points on the real axis. So, and that's key. We're only going to be testing real points. But you're right, is that every time you pass, is it true that you only need to pass 1? Because here we passed 3.
Yeah, but they have the same real coordinate.
Okay, great.
Yeah.
So every time you pass, can we say an odd number of open loop poles?
Ooh,
You switch from being out to in?
Let me think about that. Hold on.
Yeah.
So like if we pass a pole, then there's a phase, and then if we pass another pole, then that phase cancels with the other phase.
Okay, let's do S4. I think this is going to answer a lot of questions. So we're going to do one more test point. What about S hat 4? So what in the phase criterion changes?
The 0.
Exactly. So this, if we do the 4s here, 4, 4, 4, 4, this will still be some angle and it'll cancel here. S hat 4 plus 3 is still a positive number, so it has 0 phase. S hat 4 plus 1 is a negative number, so it still has 180 degrees of phase. S hat 4 plus 2 is a negative number now, so it has 180 degrees of phase. So does it matter if we pass an X or an O?
Yeah.
Try again.
I mean, it doesn't matter in terms of the phase changing, but it does matter when we're kind of computing the phase.
Exactly. Good. Yeah. So anytime the box crosses an X or an O, or an odd number of X's and O's, then we get a flip from 0 to 180. Do you see that?
Mm-hmm. Yeah.
Okay. So that is what I've summarized on the next slide. The real axis contains root locus branches, or loci, if you like, which is the plural of locuses. The segments of the real axis that have an odd number of open loop poles and zeros to the right will always satisfy the phase criterion, and so that they are in the root locus. So if you have an odd number of open loop poles and zeros to the right, you are in. If the opposite of that is true, if you have an even number of open loop poles and zeros to the right, then you will fail the phase criterion. So those segments are out. Okay? And we didn't actually necessarily prove that, but we did see it in action in our particular example problem. So let's make it nice and neat. And the way that I usually do this is I will start my pencil way off to the right. And if I go far enough to the right, there will be nothing, no open loop holes and zeros to the right of my pencil. And so this is out of the root locus. And what I do is I slide my pencil to the left, and I note the parity, the oddness or evenness of the X's and O's to the right of my pencil. Here there are 0 to the right of the pencil. Here there are 3 to the right of the pencil. So all of these points are in. All of these points are in. Once I cross this O, I've got 4 things. I've got the O and 3 X's, so this is now out again, still out. And now I've got 5 X's and O's to the right, and so this is now in forever. We don't typically write out, in. We typically shade the regions that are in. So a more traditional way of communicating this would be to shade in the real axis from -1 to -2, and to shade in the real axis from -3 onwards, usually indicated with a big fat arrowhead there. Okay? So the segments of the real axis that are in the root locus are these two. Okay, so I am going to go to the next slide, which asks the question, so far all of our test points have been close in to where all the open loop action is. And I want to now ask the question, can we use the phase criterion on test points that are very far away? So what would that look like? It would still mean drawing a little box in the S-plane and then drawing a bunch of vectors from the open loop poles to that box and then adding up all of the phases of those vectors. But if we're going to go very, very far away, isn't that the same as kind of zooming out? Hey, look at that. That's pretty cool. If I want a test point very far away, so way the hell out here, I would like you to see that as this test point moves further and further away, that all of the stuff happening here appears to shrink. And the reason that's important is because the phase criterion is equivalent to these vectors drawn from the open loop poles and zeros to the test point. And so the phases of these vectors, or the angles, if you like, as this test point gets dragged very, very far away, aren't the phases all going to approach the same value? Can you see that?
Yes, yeah. Seriously.
As this box gets stretched way the hell away, so think the analogy I like to use nowadays is if you were to zoom out on Google Maps, then the vector pointing from your house or your neighbor's house to the White House, those vectors will actually merge, or they will approximate the same vector. And that holds true for everyone in your neighborhood, everyone in the county, pretty much. So if all of the open loop holes and zeros are at finite locations, which they will be, then as we zoom very, very far away, they all act as a common root for a common vector. There are going to be, 5 of them here. So it now matters how many there are, because these phases, so theta far will approach theta far, will approach theta far, theta far, theta far. They're all going to be approximately theta far. And so if the sum of these theta fars, well, we have to also acknowledge that this is a 0, so it has a negative phase angle, or it appears as a different sign in the phase criterion. So if the balance of these thetas all sum up to, on average, 180, then the test point passes the phase criterion. And that is I would call it a vaguely hand-wavy argument for the following formulas. These formulas will tell you the path of the closed loop pole branches that they have to follow as k gets very, very large. So that's why we call them asymptotes. This is behavior of closed loop poles that are very far from the open loop poles and zeros. So this is valid only for large K. Okay. So the asymptotes are drawn as straight lines because, as we saw, as you go further and further away, all of these vectors will point in a single direction. The straight lines are drawn rooted at what is called the centroid, or sometimes called the center of mass. So if we're going to try and accurately describe the average vectors pointing from your house and your neighbor's house to the White House, we need to agree on the average location of your house and your neighbor's house. And so that would be the center of mass, or the centroid of those two houses. So the way to calculate the centroid is, I like to think of the open loop pole locations as having positive mass. And I like to think of the open loop zero locations, because of this negative, as having negative mass. And then here's that averaging. We have the number of open loop poles minus the number of open loop zeros. Okay. So this center of mass is just to give you the point that all of the open loop P's and Z's act like when you zoom very far away. The asymptotes themselves are the theta F's that I was drawing on the other slide, and they represent the angle that the vector has to point in order for, on average, the phase criterion to be satisfied. And so this is actually an iterative equation. You first solve it for k, little k equals 0, and I want to highlight that this is not capital K. This little k is merely a counter. So you solve this equation for little k equals 0, you're going to get 2 angles out of that. Then you solve it for little k equals 1, you're going to get 2 angles out of that. Then you're going to solve it for k equals 2, and you're going to get 2 angles out of that. How do you know when to stop? You only need to get as many asymptotes as you have pole branches going to infinity. So let's actually work that out in our example problem. So to answer this question, we need to find the center of mass, which is the average of the open loop pole locations. So that was, we have an open loop pole at -1, we have an open loop pole at -3, and we have an open loop pole at -1 minus j and -1 plus j. And we're going to subtract from that the average location of the open loop zeros, which is, there was only 1, so it's just -2. And we normalize by the fact that there are 4 open loop poles and 1 open loop zero. So, good news, the minus j and the plus j will cancel. And so on top we get what? 1, 4, 5, 6, -6, and then 2 up, so that gets to -4. So this is -4/3. So the center of mass is typically given in your statics and dynamics classes. The symbol with a circle with a cross through it and opposite quadrants of the cross shaded in. Please, 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 whatever symbol you use for the center of mass, so sigma A was -4/3, make sure it's different than the symbol you use for an open loop 0, because I've seen that lead to problems. So now let's work on the asymptote angles. So the formula here is 180 degrees times 2 times 0 plus 1 over 4 minus 1. So this is the little k equals 0 case. And so the reason I said that each little k gives you 2 angles is because of the plus and minus out here. So this looks like 180 times 1 over 3, which is plus or minus 60 degrees. So this means that from the center of mass, there will be asymptotes, which are straight lines drawn at 60-degree phases and minus 60-degree phases. So one more feedback question that I'd like to get from you is, how many asymptotes do we need in this problem? How many closed loop pole branches will need to go off the page?
I.
There are only 4 closed loop poles, so the answer can be no larger than 4.
So we need 3?
Exactly. We need 3 branches that go off the page because there are 4 branches total, one of which is we've already drawn, one of which lives at this X and this O, and that just travels in this region here. The other 3 need to go off the page. So this is the direction that one of them will eventually go. This is the direction that the other one will eventually go. The 3rd branch, we've actually got the asymptote right here. But for completeness, let's do the next set of asymptotes, angles. So this is, again, plus or minus 180, now 2 times 1 plus 1. So this is the little k equals 1 case. Divide by 4 minus 1. And this, if I'm not mistaken, is 180 times 3 divided by 3. So this is plus or minus 180. And that's actually exactly what we have here. We have an asymptote at 180 degrees of phase. So we can stop. We needed 3 asymptotes. We got 3 asymptotes, one of which was kind of obvious already because we'd already drawn this root locus branch on the real axis. So I think technically we could have stopped here, but going to the last one didn't hurt because it just confirmed our intuition that there is an asymptote that's going to point due west on the complex plane. So I did this in green because I want to highlight the fact that these dashed lines are not root locus branches. They are not technically part of the root locus. They are merely aids that we can use to help us sketch where the root locus branches go. What you'll commonly see me do at the end is say, okay, well, we know that the root locus branch needs to approach this and it needs to approach this. And that's about all we can get.
Can you explain one more time why it's 3?
So I think of, so there are 4 closed loop poles, which means that there will be 4 root locus branches, is the term we use. Each branch corresponds to the position, the possible positions of a closed loop pole. So one branch tells us the possible positions of one closed loop pole. Okay, so 4 poles, 4 branches. One branch, in this particular example, goes from the x at -1 to the o at -2. And that leaves 3 branches that don't have what I'm going to sometimes call finite homes. So we can think of the poles as migrating away from the x's and always towards the o's. If there aren't enough o's for all the x's, then the closed loop poles will migrate off the page.
Got
Okay,
it.
so yeah, one branch has a finite home, which means 3 branches go off the page, which means we need to calculate their asymptotic behavior. Yeah, that's a great question.
And so just to recap real quick, the asymptotes are the locations where there could be closed loop holes?
The asymptotes tell us the locations that the branches will approach as k gets big. The asymptotes are not root locus branches. They are not closed loop pole locations. They merely give us the slope or the angle and the root of where the branches will end up for large K. I would not fault you for asking what the hell I'm talking about, because right here is an asymptote and a root locus branch right on top of each other. And I'm going to say that's okay, because this asymptote still tells us the behavior of this branch as K gets large. It also happens to tell us the behavior of the branch as K is small, but that's incidental. That's coincidental, if you will.
Okay, I got you.
Okay, yeah, and it's an important point, because I don't want to see people, I don't want to see this.
It's just that somewhere on the asymptote, wherever, somewhere there is a branch, not necessarily the whole thing.
So, I mean, think about where you first learned about asymptotes. It's that the limit of a function as it approaches some number is the asymptote of that function.
Sure.
These asymptotes are the limits of these 2 root locus branches, if you like.
Okay.
Yeah, good question. Okay, that brings us to 9 o'clock and the end of this lecture.